This video is about the motion group of a cube. What we're going to basically be doing is we're going to be talking about the rigid symmetries of a cube. And what a rigid symmetry or a motion is that we're going to be thinking of our cube as a solid cube. So let's draw a cube over here. Just a real quick sketch of a cube. And essentially a rigid symmetry is going to be a way to move the cube so that it lands back on itself. In other words, once we've done the motion, the cube is physically in the same place. So once we finish the motion, the cube is exactly where it started. In terms of its physical position. Now, I want to think about what that means for just a second. Well, what that basically means is that, well, first of all, we've got 6 faces, a top, a right, a bottom, a left, and a front, of course, and a back. And if I'm wanting to rotate this cube and have it land in the same spot, well, basically what that means is I can rotate it in that direction, which would kind of be around the y-axis if we're thinking about a standard x, y, z setup, or I can rotate it in this direction, which would be kind of rotating around the x-axis, or of course I can rotate it around the z-axis, going that way. Well, trying to draw pictures is obviously kind of complicated, so what I really want to do is I want to look at a cube that I can pull around in real time. So over here I've got a Mathematica cube where the faces are labeled top, bottom, front, back, left, and right in the usual particular way. And what I want to first of all notice is that if I want to keep the top side on top, so I want to keep this side on top, then what I can do is I can start with the front and I can rotate 90 degrees in a counterclockwise position, and that puts the left side in front. I can rotate 90 degrees again, so I've now done a 180-degree rotation, and the front and the back have swapped places, as have left and right. And I can rotate another 90 degrees, that would be 270 degrees total. And now the right-facing front, the 60-degree rotation, obviously I'm back to the original orientation of the cube. And so for the top being fixed, there are 4 rotations that I can actually do. Well, of course, I can rotate this cube 90 degrees in this direction, and the back side becomes the top side of the cube. And once I have that, again, there's a 90-degree rotation, a 180-degree rotation, a 270-degree rotation, or a 0 or 360-degree rotation. And so there's 4 different rotations once I have that back side on top. The same thing happens if I put the bottom side on front. This is my 0-degree rotation, my 90-degree rotation, my 180-degree rotation, my 270-degree rotation. 360-degree rotation is the same as not rotating at all. And then I can also put the front side of the original front side on top. And again, I have the 0 degree rotation, 90 degree rotation, 180 degree rotation, 270 degree rotation, 360 degree rotation, which is just like not rotating at all. And then when I do one more 90 degree rotation, and this one, of course, I come back to the do nothing. Of course, I could also rotate this direction and put that left side on top. And again, once the left side is on top, we have a 90 degree rotation, a 180 degree rotation, a 270 degree rotation, 360 degrees, which is exactly equal to not rotating at all. And of course, I could have also done, going back to my original cube, I could have rotated the cube to make the right side become the top side. And then, of course, there's a 90 degree rotation, a 180 degree rotation, a 270 degree rotation, or 360, which is exactly equal to rotating 0 degrees. So no matter which of the 6 sides I choose to put on top, we get 4 rotations that are also solid, that are also rigid symmetries of the cube. So what that means is that we now have the following basic idea. And I'm going to make this stuff go away because I need a little bit more room to write. But what we now know is that for each face on top, there are 4 rotations that fix that top. And there are 6 choices for which side got moved to the top. And so what that means is that we have six choices for top times 4 rotations equals 24 rigid symmetries. Well, that's essentially what the author has done when he starts this section, and he says a cube has 6 sides. In particular, if a particular side is facing upwards, there are 4 possible rotations of the cube that will preserve that upwards facing, and hence we have this many. So we have just proved this particular theorem. Now, what we haven't done yet, and it's an important idea, is we haven't addressed a very important question. What group is the motion group of a cube isomorphic to? We also don't have yet a way of explicitly writing the elements of this motion group. So the other question that I want to be thinking of is, this should be question 2. How can we explicitly describe each of the rigid symmetries? Of a cube? Because if I can describe them, then we can actually work with the group. And the critical idea that I want to set up right now is that using permutations will give us a way of describing the symmetries. And once we can describe the symmetries, we can then simply use permutation composition to explicitly describe what group we are looking at. Those will be topics of future videos.